So we are happy to have Jake Solomon from the Hebrew University, and he will speak about counting holomorphic disks with boundaries on the Chiang Lagrangian, and probably you will tell us what Chiang Lagrangian is.
I hope so, yes.
Thank you. Go ahead.
Thanks a lot for the invitation. It's an honor to speak in your seminar. Zoom is getting in the way of my notebook. I'm trying to get it out of the way. Oh well. Try to deal with this. Okay, so here we go. Let's suppose that we have a symplectic manifold. As usual, we'll have so omega is a symplectic form. And J will be an omega tame almost complex structure. Okay, and then we'll have a Lagrangian submanifold. And oh, by the way, if there's anything which I say which isn't clear or which causes some question, please interrupt me. It's much more fun to talk if the people talk to you. So I'm going to assume for simplicity that like the L is sort of nice, let's say connected, spin, so specified spin structure, and also let's assume there's a cohomology sphere, so the real cohomology L is same as the real cohomology as the N sphere. There we go. So let's assume that N is the dimension of everything here. So the real dimension of X will be 2N. Okay, so then sort of the goal of open Gromov-Witten theory at least in genus 0, is to, you want to count maps from the disk which map to the symplectic manifold and map the boundary of the disk to the Lagrangian submanifold, which are J holomorphic. And you want to, of course, count these things up to an appropriate notion of isomorphism. Well, I mean, sometimes the space of such maps will be will not be zero dimensional. So you might be also impose some conditions that some given cycles on X and L. And the idea is that you'd like this count to be independent of J, and it should also only depend on the homology class of the cycles. Okay, so a schematic picture would be that you have here a disk. This is sort of Lagrangian submanifold, and this whole notebook is a symplectic manifold. And then we like to consider some maps U, and the image will look something like this. It'll be sort of a disk which has boundary on the Lagrangian submanifold L, and it may pass through some cycles on L, and maybe also some given cycles on X. And then you hope to get a finite number of such disks, and you want to count them. And this will give you, on the one hand, an invariant of the symplectic geometry of L, but also maybe some kind of interesting structures, which can sort of algebraic structures which may come from that. And maybe we see later that actually there's some number theoretic phenomena which arise here. Okay, so that was a bit unexpected though. So this is a nice idea, and it's kind of been around since the beginning of Gromov-Witten theory, but there are sort of two problems which prevented the development of this theory. So the first problem was disk bubbles. So roughly speaking, what can happen is that you have a disk, a holomorphic disk, which, as we drew above, but then at some point you can say change one of your things which you don't want your count to depend on. So you could change J, for example, and then the disk could start to develop. Since you change J, the disk will sort of, could change a bit, and at some point it might develop a sort of a neck. Okay, so it might develop a kind of a neck here in the middle. And then you keep on changing J, and then this neck squeezes to a point. This is what you call disk bubbling, because a single disk splits into two, like a kind of a stable degeneration. And then eventually, after this point, after the disk bubbles off, then there's kind of nothing left. And at this point, you expect the count to change. So then it seems sort of more or less hopeless to count such holomorphic disks. But there's sort of an idea for how to solve this. Okay, so maybe I should say, are there any questions at this point, or?
Well, I think if people have questions, they will unmute themselves. So it's kind of.
Okay. So the solution idea is that sort of informally that that we can continue counting something which is not just a disk or a stable disk. So this would be like what you call a stable disk. kind of like a stable map, stable disk map, with boundary. Okay, so then you can continue counting something which is somewhat more generalized, which would be sort of keep track of how the sort of boundary components of different disks link with each other in a sense, or moduli spaces of boundary components of disks link together. Okay, so you have to somehow, so these disks, after they, at some point are intersect at a sort of nodal point, they can just move apart. Then you have to keep track of the fact that once upon a time they were together, and you do that by sort of keeping track of some chain on L, which in a sense its boundary is the boundary of, say, one of the disks, and this notion is called bounding chain. Okay, and so this replaces nothing with something and allows the count to continue invariant. And then there's sort of like formally, you want to look at bounding, well, I should say cochain at this point, is a solution of the Cartan equation, in the Fukaya infinity algebra. Of their Lagrangian submanifold. So I'm probably not going to go into a whole lot of detail about what this means, but it's a well-developed theory, and sort of maybe something one should ask is, what about choices? Then
your L is compact, or your X is compact. Is there any compactness?
I should say
it's same at infinity, so then it doesn't have to be compact.
Yeah, I mean, it's not necessary really, I guess, but I mean, usually sort of current state is that I mean, the published stuff is all assuming compactness, but sort of the idea of a bounding cochain is nice, but then it actually, to turn this into some kind of invariant count, as opposed to just defining something like Floer homology, you need to be able to choose the bounding cochain canonically, because the answer will depend on which bounding cochain you choose a priori. Okay, so the theorem, which is due to myself and Tukachinsky, I guess it's an archive around 16, is that there's a canonical okay, and this bounding cochain somehow includes the cycles on L, which are supposed to cut down dimension. And it's sort of like, maybe I should say, it replaces the cycles on L. So in a sense, like if you were thinking in terms of cohomology, you would say you should look at a cycle. But if you're looking in this kind of, have to correct this bubbling phenomenon, then it's no longer appropriate to look at actually a cycle, but you should look at a chain, but which satisfies sort of non-linear version of being closed, which is the Morikatan equation. And these cycles, well, they're really not cycles. Maybe in the end, you're sort of forced to consider only points. Okay, but you're allowed to have as many points as you want.
What do you mean canonical? Yeah, I'm always confused when people say canonical.
So I should say canonical up to gauge equivalence.
Up to gauge equivalence of what?
So there's a notion of gauge equivalence.
You mean for
bounding.
solutions to Maurer-Cartan equation?
Exactly.
Okay, all right, I see.
Exactly. Okay.
And
So
this is for things which are cohomology spheres.
This is for, right, so this canonicity uses the cohomology sphere condition. Okay, so there's ways of getting more general results. So you can remove this condition. For example, if you assume that L is, say, the fixed points of anti-symplectic involution, or maybe that's in our paper as well. I think Tukachinsky has a forthcoming result in which the cohomology of the ambient manifold subjects onto the cohomology of L. Different situations in which you can find a canonical bounding cochain. A priori, it depends on some kind of obstruction theory, which the obstructions lie in the cohomology which vanishes for a sphere, or in the involution invariant case, then you can kind of, some of the obstructions vanish because of the symmetry, and you can require less cohomological restrictions. Okay, but today I'm going to be talking about the Chiang Lagrangian mainly. So that is a homology sphere, a cohomology sphere. So a real cohomology sphere, rational cohomology sphere. So this is going to be enough for today. So problem 2 is that what a collapse of the boundary. Okay, so you're counting these disks, and as you change J, the boundary of the disk might get smaller and smaller, and eventually contracts to a point. And after that point, there's just nothing left in your count. And the idea of the solution is that
what do you mean nothing is left? I'm a bit confused. Like if you do not count, your empty boundary is not a boundary, or what, in your sense? There are some cycles without boundary on your L, you don't count them, yeah?
So maybe the way to say this is that this is like, this is kind of codimension 1. And if you remove the condition that it intersects the Lagrangian, then it will, the dimension will be far too large. Because intersecting the Lagrangian is a kind of codimension n condition on all holomorphic spheres. So there's kind of, what are you going to count after this? So this is kind of a boundary thing of the moduli space. This is where the boundary collapses. And then you sort of fall off the boundary of the moduli space, and there's nothing left to count. So the solution idea is that you can choose a cycle C on X such that the boundary of C is equal to L, and then count also J holomorphic spheres say that intersect okay, so picture would be something like this. So this will be L as usual. And then we draw here C. I'm getting a warning message that my internet connection is unstable. I hope people can still hear me.
Yeah, so far so good. Yeah.
Okay, great. This is maybe like a rough idea of C. And then sort of after counting things which just end on L, we can count things which sort of end, you know, but they sort of go on and they end inside of C now. Okay, so now instead of just getting stuck here, we can count some kind of moduli space which has dimension, the right dimension, right? Because C has dimension 1 higher than L, and now spheres passing through C will kind of naturally complete the moduli space of disks on L, and which have this boundary component, which is consists of disks. Sorry, with spheres intersecting L. They can also, if you allow them to also intersect C, then you get a moduli space without boundary, and you can count. So you have to count also such holomorphic sphere maps. Okay, and so the formal idea, which in this, the sort of clean way of formalizing this is to look for kind of okay, you have a map from the cohomology of the nth cohomology L to the n plus first cohomology of x relative to L. And I want to choose a kind of right inverse map here. This is the sort of co-boundary, and I think it was the right inverse or left inverse. So we choose some P R from H n plus 1 relative cohomology. Such that when you compose it with the boundary map, you get the identity. Okay, so this you can think of it as being given by integration over C. But this makes it clear that your choice is only a cohomological choice. So it's easy to keep track of, and you can also follow what the influence of this choice is on the invariance you get in the end. Okay, so upshot of all this. So I guess this formal solution comes in paper archive 19. And the upshot is that we get some invariants which a priori give you a real number, because this formalism uses differential forms and stuff. We need cyclic symmetry and okay, what is this? What is the meaning? So for by the way, I should have said here that that these right these J-holomorphic maps you usually want to fix the homology class. No, it's forgetting something here, which belongs to the second homology of X relative to L. Okay. So here, beta, second homology class, and K is some number. You think of this as the number of boundary point constraints. Because the way this formalism works, you can have point constraints in the boundary and some positive integer is the number of interior constraints. Number of so these cycles, which they're given by cohomology classes in the relative cohomology of X with respect to L with a slight twist. That's the hat there. And these are invariant. They, depend only the deformation invariance of the symplectic. So they're symplectic deformation invariance. So even if you change the symplectic form in a continuous family, they're not going to change.
Jake, I have, maybe it's not a good time to ask a question of this type, but there is a version of usual Gromov-Witten theory for algebraic varieties, which kind of, it's not really symplectic geometry, it's rather algebraic geometry. Is there a version of the relative theory if everything is algebraic?
So the situation is not bad if we work over, if say, typical example is you take sort of X to be in, say, projective algebraic variety. Sorry, maybe I should say the C points of projective algebraic variety. Well defined over. Okay, this is not quite right either, but okay, defined over R. Okay, and then you sort of look at the maybe it's better to say the restriction of scalars. Okay, so I mean, but maybe say, let's just make it short and say insert base change to C, yeah. And L will just be sort of like the same thing, but just without any base change, the real points. To the real points. And then you have, this is a typical Lagrangian submanifold. In parentheses, right? So in this case, one can define things more or less algebraically in different levels of generality. You can even work over some other fields in some situations, finite fields or number fields. The invariant then becomes not a number, but a quadratic form. But not really talking about that now. But in general, if you have a Lagrangian submanifold, which is not, say, the real points, it's hard to think of what really. So I guess you could have sort of like a holomorphic symplectic manifold, and then the Lagrangian holomorphic Lagrangian submanifold. Then there's a theorem which says that there really aren't any holomorphic disks there. I mean, at least not generically.
Yeah, but that's the whole point. Generically, but there is a very interesting and quite extensive theory when you consider one parameter families.
One parameter families, yes. Okay. I agree. And one parameter family is probably some interesting theory. Not sure. Yes. So there might be one possibility to do that algebraically. For some reason I had some feeling that that wouldn't work, but I'm somehow forgetting it now. So maybe it's okay. Okay. I agree. So anyway, the question is, so this definition is rather abstract, and can you actually can you calculate any of these invariants? This is sort of the main question now. And so one example that you can look at is that, for example, say this is real projective space. So this was also in that paper 19. And you can compute everything. And the idea is that, so the ingredients are, first of all, sort of in degree, sort of a beta is the generator in the relative second homology here. You can compute this, like, I mean, sort of OGW, let's call this beta 2 and sort of nothing, right? Is that like the number of lines through, like, real lines through 2 points on RPN. We all know that's so maybe oriented lines because it's a disk, right? So there's 2 of them. And then sort of there's an open WDVV equation and sort of open GW axioms. And this is this allows you to determine everything recursively. So sort of crucial invariant here is that you have this real algebraic geometry. Okay, it's pretty basic real algebraic geometry. There's other cases where it's more involved. And And you can use this as sort of a input from which you can then compute invariants. And the example I want to talk about today is specifically so there's, here's B is, an anti-symplectic involution. Which is given by complex conjugation. And this, as I was saying, it makes the abstraction theory makes it easier. And the question was like, is there some case where you can take L, which was not the real points? So the case I want to consider today is the projective 3 space, and L is the Chiang Lagrangian. Let me say briefly what that is. So it's a homology sphere. It's so it's pi1 is order 12. It's the quotient of S3 divided by the binary dihedral group or something like that of order 6. And how do you construct this? So I mean, maybe I should say the principal attraction for us of this example was that I guess it's due to Evans and McKilly. L is not fixed by any anti-symplectic involution. Okay, so there's kind of no hope to think of this in terms of like the real points of an algebraic variety or something. And so more explicitly, what is this thing? So let's think of, well, X, can you think of it as being the symmetric power of CP1, and then L, so think of CP1 as being a 2-sphere, and L will be the following thing. So in other words, unordered triples of points on the 2-sphere. So L sitting inside this will be given by triples like A, B, C, such that A, B, and C are equidistant and lie on a great circle. Uh-oh. My pen has run out of batteries. It'll take 5 seconds to recharge. Any questions? Well, I'm charging my pen.
Yeah, I mean, probably there are some properties of this Lagrangian which kind of make it special. Yeah, it's not a spherical object in the Fukaya category.
Well, I guess it's in most cases it's probably going to be a trivial object. If you work over some like with appropriate coefficients, you can get it to be to generate the whole category. This is, I think, these are things results of Evans-Lakilly. I mean, I guess if you want to have a hope of thinking of this in terms of the Fukaya category, then probably, at least if you're looking at characteristic 0 coefficients, then it's probably a good idea to like work over an Novikov ring instead of an Novikov field. But then the category gets enlarged and it comes with a cost. It'll be some kind of torsion on it. Just like for that matter, RPN or RP3. Okay, but its topology is obviously different. And well, we'll see that its invariants are kind of dramatically different. Okay, so this is the thing that you're after. And so what do we know about this? So first of all, so this is kind of results of okay, a lot of people. Stop the student. And this is all from this here, which says that first of all, well, I mean, there's different things here. One of them is that the open WDVV equation and the open Gromov-Witten axioms and so on. And of course, knowledge of the usual Gromov-Witten theory of CP3 reduces all the OGW of the Chiang Lagrangian so CP3 and our Chiang Lagrangian to 3 initial values. OGW 1, 0. I should imagine the relative second homology of x with respect to L here in this case is still Z. So you have OGW with, but the sort of the mass level index here is going to be different than for usual RP3. So they're going to say mass of 2 disks, for example. So it's given by times 2 instead of times 4, like for RP3. So that's why you can have disks which are, this is counting disks with 1 boundary marked point. Sorry. This is beta. This is the generator of H2. And then I have 1 boundary marked point. That's boundary marked point. Okay. And so, and also OGW 1, 0, and the cohomology class of the symplectic form squared. And finally, OGW of cohomology class of the symplectic form cubed. But now this beta is going to be no longer the generator, but the degree 2. So you get these, you can reduce everything to these 3 basic invariants. And B, that, so we give a general criterion, but in case, in the case of this Chiang Lagrangian, basically the general criterion says that OGW, so let's call these the basic invariants. So part B is that the basic invariants actually just wind up counting disks. No need to consider bounding cochains. Okay. And finally, we actually have to compute these things. And the answer is, this one is 3. This one is 1/4. Sorry, here. And this one is oh dear, I'm forgetting the sign. 1 second. The hardest part of this calculation was, of course, computing the sign. -1. Okay. And okay, so these computations use the theory of axial disks. So I guess one thing to keep in mind is that like this is kind of an orbit of SU2 in the sort of the third anti-symmetric power of third symmetric power. Of the defining representation C2. So these axial disks, they arise from kind of one parameter subgroups of SU2. Okay. And thinking about these disks in this way kind of allows you to really kind of envision, like to really kind of imagine how they look, and so you can actually use this very like hands-on picture that you get to figure out even the signs kind of very precise. I just want to show one example of the recursion relation. So there's 3 recursion relations. So how do you, this open WDVV thing gives you, together with the different axioms. So I'm not going to tell you the full general formulation of the open WDVV. It happens for every x and L. But for this particular case, I can show you one of the 3 recursion relations. There's a specific reason for this. This. So here's one of the recursion relations. And at first glance, it doesn't look very different than any other WDVV kind of relation. I hope it's visible. So here the gammas, by the way, are kind of the classes. Gamma I is the class of omega I inside of H2I XL. I never said what this meant, but it's basically relative cohomology. And the deltas are sort of the GW, this is the regular Gromov-Witten invariance. not going to say what they are. And this is the class of omega to the I in the absolute cohomology. Okay. And okay, so this looks pretty standard, but why pay attention to this? Because unlike in most cases, you cannot isolate sort of, this is, by the way, this holds true. So this is for k greater than 2 and L, sorry, yeah, and L greater than, no, sorry, it should be for, yeah, maybe have to go this, okay. Right, yes. So the point is that you have to divide by this number in order to sort of get out the thing which you want. Okay. So there's this recursion which involves dividing by an invariant. And one can see part of the result of the paper is that you can compute from different things that this invariant gamma 2 is equal to 35 over 64. So we divide by this thing, and you know there's some on the other hand, and what do you get? And of course, it's done recursively. So each time you go up to the next beta and k, you have to divide more. Here's some examples of numbers we get. Paste it back. Okay. Hope this is visible. So if you just look at these numbers, you notice the denominators are always powers of 2. Okay, so you're dividing by 35 or 64, but still the denominators always stay powers of 2. And you might think, well, this may be just some kind of soft phenomenon, but for example, if you change the sign of this invariant, say, or any one of the 3, this phenomenon will be destroyed. In fact, it seems that if you know 2 of the initial values and you require the denominators to the powers of 2, this entirely determines the third. But somehow we can't prove this. It's just by numerical experiments, it seems to be true because you need kind of an infinite number of conditions to determine this. There's kind of some kind of arithmetic structure which goes on in this recursion relation, which we don't really understand. Also, if you look at the signs here of these numbers, so the results are presented in columns of length 16 on purpose, so you can see that the signs repeat themselves after 16. So it's plus, plus, minus, 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 plus, 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 minus, minus, plus, 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 minus, 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 and then it starts over again after 16. And another interesting thing which happens is that sort of the numbers, well, at the beginning, they're not very regular, but then after a certain point, say around 8 or so, they basically, at least absolute value keeps on increasing and increasing. And then at 16, suddenly it jumps down. Okay, so absolute value increase. Here we jump down by a factor of maybe 100. And then again, when you go to 17, 18, 19, 20, and so on, the absolute value increase. And then you jump down again by a factor of 100. And again, you increase. So every 8, you have this jump. People say for some reason this looks like coefficients in kind of modular form, but I don't really understand this well enough to have an opinion. Another thing, which is interesting here, is that when you, so the sphere, so I said before in this, the solution to problem 2, involves counting disks and spheres together. It depends on a choice of some map of cohomology groups, right inverse. So, but no matter which PR you choose, one can show that these invariants, many of them don't vanish. So this, in the previous examples, for some reason, they always vanished. Invariants counting disks and spheres together don't vanish. Okay, so this is in contrast to previous computations. So not all the, actually it turns out not all the invariants depend on PR, only the ones which, so what I mean by invariants counting disks and spheres together, only the ones where sort of OGW 0 and beta, where beta belongs to the image of the map from H2 XZ to H2 X relative. Okay, because this is kind of, if you have a boundary constraint, then the boundary cannot collapse. This can be seen. And also, if you don't come from a spherical class, absolute homology class, then you cannot collapse the boundary also. So the other invariants don't reflect this, but so in previous computations, the moment you get no boundary constraints and beta in the image of this map, oops, beta in the image of this map, then the invariants always vanish. But in this case, the Chiang Lagrangian, they don't vanish. So I guess I'm out of time. Thanks for listening.
Thank you very much. Jake, I'm confused in kind of basic question. Is there a quantum differential equation for the generating function of either disks or disks spheres together?
So
closed theory which involved this mirror symmetry periods and maybe some arithmetics of those periods.
the answer is yes. There is a quantum differential equation. It's, so I mean, it applies kind of to a generating function for these OGW bar things, which, I mean, some of them count only disks, and some of them count disks and spheres together. I mean, the ones which need to count spheres as well, which are the ones where you have no boundary constraints. So this is kind of no boundary constraints. And where beta is spherical, where this class actually comes from a sphere, those you need to count spheres as well. Okay, but kind of these invariants all fit together in a single recursion, and actually these this like recursion is basically a way of writing the quantum differential equation, if you like. There's a kind of a flat connection on a certain extension of the usual quantum cohomology.
And but the mirror symmetry doesn't play any role. And I mean, these invariants, can they be interpreted in terms of some periods?
So there's recent work of I don't want to say a theorem because I'm not going to get the exact statement, but work of Kai
Syllabug.
no.
Okay.
I'm trying to remember his last name. It's embarrassing.
Buchtenberg.
Thank you.
Well, it's a difference between the expert and yeah.
Sorry, yeah.
No.
I apologize. And I probably misspelled the name.
Okay.
But I'm trying to remember. There's a spelling mistake I always make here, but okay. Should have preferred in advance.
But what kind of?
Okay, so he finds like kind of a variation of I guess semi-infinite Hodge structures, which here we go.
That's the guy who gave a talk here. Okay. Yeah.
I guess so. Okay.
Yeah.
Variation of semi-infinite Hodge structures. Yeah, so probably, yeah. And yeah, so I mean, in theory, if you could figure out this variation of some infinite Hodge structures, then you would be able to reconstruct at least. So I'm not sure exactly how far it's been pushed. It's mostly, I think, kind of developed in the Calabi-Yau case, but it should also work in this case. But there's maybe some information which it's not clear how to determine. So maybe the predictive power is not 100% at this point. And maybe it's not either clear exactly what's the mirror to the Chiang Lagrangian, but I mean, I'm pretty certain that using the usual SYZ kind of heuristics, one should be able to arrive at some kind of matrix factorization.
But you said this is zero, right?
What's the question, Lena?
And this gives you zero object in the Fukaya category. Didn't you say earlier?
Right. So it's the zero object in the Fukaya category, but if you work over a Novikov ring, then it becomes kind of torsion object. Well, mirror symmetry is maybe not super well understood in that case, but I mean, I guess I should say that with one of the authors, Sela, we're working on sort of getting these invariants out of this matrix factorization. Well, I mean, not in this particular case yet. And perhaps, and presumably you can attach to this matrix factorization some kind of variation of Hodge structures or extension of variation of Hodge structures. So, but the exact, I mean, the full details of this are not yet visible.
You know, in the closed case, when this algebra geometric story, which I asked you at the very beginning, there are some blow up formulas for the closed Gromov-Witten invariants. I'm just curious how far this can be extended in the relative case. When you
I think there are some works like this. I'm forgetting the name of the authors. I think it's mostly in the case when you have an involution. I don't know if people have worked it out in the case of sort of this kind of, so even when you have an involution in higher dimensions, you need the bounding cochains. If you have dimension 2 or 3, then you can just get away with an involution. Sort of all the obstructions vanish. But in higher dimensions, you still need some kind of cohomological conditions, and but like in the real setting when you're in dimensions 2 and 3, I think there's some result. I'm forgetting the author's name. I apologize. Which computes the chain under blowups, and it kind of analogous to the closed theory, I think, as long as, right, if you blow up at a sort of point on the symplectic manifold away from the Lagrangian. I guess it'd be more complicated if you do a sort of blow up relative to the Lagrangian. That's probably a more interesting case. Because then, I mean, but sort of, this probably requires some kind of relative Gromov-Witten, open Gromov-Witten theory. So in the case when sort of everything happens away from the Lagrangian, then this is maybe a little bit easier. And when it happens on the Lagrangian, then, well, currently there's not really a well-developed relative theory of this, but kind of expect it exists. It might be quite a bit of work.
All right, more questions?
Yeah, I can ask a question. So in these cases you are talking about for these real Gromov-Witten invariants for the case of involution, do you get the same answer, or let's say in this RPN case, or
same answer as,
like, I don't know, like there's like Zinger and stuff, right? They have this thing about like real Gromov-Witten invariants.
right? So Zinger, for example, okay, in dimensions 2 and 3, then they are computing basically the Welschen-J invariants, which will show what we are computing. And we get the same answer, of course. I mean, maybe not of course, but it's the same equation. I mean, basically they proved this equation, which, okay, they found a way of just doing a recursion for invariance without boundary, without kind of real constraints, only like complex conjugate constraints. And that gave a partial answer. And then afterwards, they proved more or less the same equation, but in a kind of real setting, only dimension 3. In the higher dimensions, so there's kind of the bounding cochain formalism gives you a great deal more invariance than you can get if you're only willing to use the kind of real formalism. So for example, in the bounding cochain formalism, you can have real constraints. In the other, you can only have complex conjugate constraints. And kind of only the odd powers of the symplectic form are allowed. So, okay, in general, they have to be kind of anti-invariant under the symplectic involution. So if you have like even powers of symplectic form, then if you just count real curves through those constraints, even forgetting boundary constraints, then the invariant won't be, sorry, the number won't be invariant. It will be subject to this bubbling phenomenon. And so in order to get an invariant, you actually really have to use the bounding cochains. So for the cases when our invariants are kind of the same thing, then it coincides. But sort of in this paper with Tukachinsky, we're computing like many invariants which simply were not defined in the real formalism. Even for like CPN, RPN.
Okay.
Did that answer your question, you know?
Yeah, sure. And my other question is, I think they also do higher genus, right? In
Yes.
this field setting. And is there any hope of having higher genus in your setup?
Yes. I'm working on it with a graduate student.
Oh, okay.
At present.
And is it still just like choosing bounding cochains and things like that, or is there like really new stuff?
Well, I mean, it's considerably more, you don't really know, I mean, the Moore-Catani equation really doesn't make sense anymore for higher genus. You have to kind of figure out like a kind of different algebraic framework. So that's what we're trying to do, basically. I have some kind of idea how to do this, and I hope it works.
So, Lina, are you happy?
Yeah.
Okay.
Yeah, just one more question. These numerical things like these denominators being powers of 2 and so on, does something similar occur for RPN? You said you can compute things on for RPN also.
So there's like a geometric reason. Okay, first of all, like in all other examples which I know, even like regular closed Gromov-Witten theory, sort of the invariants always kind of grow monotonically with degree beta. So certainly for RPN, but also sort of like I looked at a lot of different computations in the real case, and they always grow monotonically. So this kind of periodicity, really, I asked Rahul Bhattacharya if he saw this kind of thing in a complex case. Haven't heard. I would be glad to hear if there's other examples where this kind of thing happens. The same with the sign, like periodicity, and in terms of the denominators, there's kind of a geometric explanation for it. Actually, if you can see from the, I should have said powers of 4 here. Like the denominators are actually powers of 4. And this has to do with the fact that the homology, this first homology of the Chiang Lagrangian happens to be Z mod 4. And these denominators, essentially what they reflect is that when you choose the bounding cochain, you have to trivialize some kind of torsion class. And so you have to like take some like class, like kind of chain, which trivializes the 4 torsion class. And well, you have to trivialize like 4 times the 4 torsion class and then divide by 4. And that trivializes over the rational numbers. And this leads to the denominators of 4 here. Now for RPN, of course, the first homology is 2 torsion. But also the disks always come in pairs. So the boundary of a moduli space of disks will always be like at least twice the 2 torsion class. And so when you trivialize it, you don't have to divide by anything. So it turns out, and numerically, so I don't know how to prove this rigorously, but sort of heuristically, it makes sense that in RPN we get for the only real only like you have no interior constraints, only boundary constraints, all the invariants turn out to be whole numbers for RPN. So this is like the first time that we ran into a case where the numbers without interior constraints turn out to be fractional. And the fractionality reflects the fact that the bounding cochain is not a integer cochain. It's actually a rational cochain, and you can see the denominator should be like powers of 4. And that's what you actually find in the computation. But the reason for this, of course, is mysterious, because when you look at the computations, you're getting powers of 3 and 7 and who knows what. So from the recursion, you're defining by this, you always have to divide by this thing which multiplies the thing you're computing. And this thing has numerators of 35. So you'd expect to get denominators like powers of 5 and 7, and somehow all just cancels out.
Okay. And for the signs, is there any explanation or?
I have no idea. I'd be really happy if somebody had some way to explain that. I mean, I should say that
RPN, are they all positive? In the case of RPN, are they all positive?
In RPN, I think they alternate plus minus plus minus.
Oh, okay.
But I mean, when I saw the signs at first, I sort of assumed there's just no pattern at all. But then I thought, check a little more carefully, and there was a pattern. But it's definitely, yeah, it's not just plus minus plus minus.
Okay, more questions? If not, thanks, Jake.
I can ask one question.
All right. So,
At some point you said you prefer these bounding cochains to be points. Why do you like points more than other things?
Okay. Well, okay, so I mean, basically in the case we're considering, maybe it's kind of just what you expect, because we're talking about a homology sphere. So you can either have the class of you can either have the unit, which of course you expect to trivialize the invariant, or you can have the class of a point. And indeed, this is what happens. So, but it's not the class of a point. It's like the class of a point, but then with all kinds of corrections to it to make it so like to first, like the 0th order will satisfy Morikawa equation because it's closed. But then when you actually have to get the higher order corrections coming from the nonlinear part of the Morikawa equation, you get all these corrections to being closed. And so it's no longer closed. It's just a bounding cochain. But it's sort of the only thing there. The question is like less clear in the case when you have L is fixed by an anti-symplectic involution. Because then, in theory, like the cohomology at L could be more general. But still, somehow the theory sort of forces you to look only at point constraints. Because sort of the way you classify the bounding cochains is given by sort of integrating over L. So this kind of integration over L map classifies the different bounding cochains. The integrals is invariant under gauge equivalence, and in fact, it's enough to classify under the appropriate assumptions. On the other hand, you can see that if you had any way of, there's a kind of like a formal argument which shows that if you had any way of like having the bounding cochains which depend on more parameters, somehow manage to get them to be in, canonically depending on, say, 7 parameters, the only parameter which would matter and which would change the invariance is the integral over L. So in theory, bounding cochains could depend on more parameters, but it seems like from it's a very simple argument. I mean, but I don't know if there's like time and interest to see it, but it takes about 3 lines, but you just kind of take the derivative of the superpotential and you see that like the derivative with respect to the parameters of the bounding cochain gets multiplied by the integral of the bounding cochain over the Lagrangian. So if that integral is trivial or doesn't change, then the derivative with respect to that parameter will be trivial.
Oh, okay.
So it's written in this paper from 2019.
Okay.
Tukachinsky.
Thank you.
Okay, so I think now it's time to thank the speaker for the talk. Thank you, Jake. And I ask you to send, say, me or Lina a PDF file of your talk, if you can.
Yeah.
All right.
Sure, I'll be happy to do that.
Yeah, thank you. And